The sky stretches endlessly above us, a vast tapestry of mystery that humanity may never fully unravel. Since the earliest days of our existence, people have gazed at the stars, weaving intricate tales that transformed these distant lights into divine beings, powerful gods with supernatural abilities capable of shaping the destinies of humankind. These ancient myths, filled with wonder and reverence, painted the cosmos as a celestial stage where deities played out their grand dramas, a narrative that captivated the imaginations of generations. However, as science emerged from the shadows of the Dark Ages, it gently guided us away from these enchanting stories, urging us to separate myth from reality. With a newfound clarity, we turned to the laws of nature we could discover and test, seeking to understand the universe through logic, evidence, and reason rather than divine intervention. Yet, as our scientific knowledge deepened, an astonishing phenomenon occurred. The ancient tales of gods and creation began to resonate with an unsettling realism, prompting a profound and timeless question. Could all these legends passed down through millennia point to a singular truth, suggesting that somewhere beyond the stars, a supreme creator might have designed this vast and intricate expanse we call the universe? When we think of genius, certain names immediately come to mind. Towering figures like Isaac Newton, Albert Einstein, and Nikola Tesla, whose intellect illuminated the path of human discovery and forever altered our understanding of the world. Yet for all their brilliance, these individuals remained human, marked by imperfections, doubts, and moments of error that remind us of their mortality. Albert Einstein in particular stands as a monumental figure in this journey. His relentless pursuit of cosmic truths, yielding predictions that propelled humanity forward in its quest to comprehend the universe. His achievements were nothing short of extraordinary, reshaping the very fabric of scientific thought and opening new frontiers in our exploration of reality. However, alongside these monumental triumphs were mistakes he later acknowledged, including what he famously described as his biggest blunder, a misstep that would ripple through the history of science and spark debates that continue to this day. To fully understand this pivotal error, we must travel back to a time when Einstein was not yet the unrivaled icon of science he would become. It was 1905, a year that would mark a turning point in physics, when Einstein first unveiled his theory of relativity, a revolutionary framework that challenged the very foundations of Newtonian physics, which had dominated scientific thought for over 2 centuries. At the time, the scientific community was deeply rooted in Newton's laws, which had provided a reliable model for understanding motion and gravity in the universe. The introduction of relativity, with its radical ideas about the nature of time and space, was met with immediate skepticism, a reaction that is in many ways the hallmark of the scientific method. Science does not readily accept new ideas. Instead, it seeks to dismantle them through rigorous experimentation and testing, only embracing a theory when every attempt to disprove it has failed. This stubborn, sometimes frustratingly slow pursuit of truth is the delicate boundary that separates authentic science from pseudoscience. True scientific principles demand consistency, grounded in laws that can be tested and verified, not in explanations that rely on random chance or coincidence. Thus, when Einstein's theory threatened to upend Newton's long-standing legacy, the scientific world responded with intense scrutiny, subjecting relativity to every conceivable test in an effort to find its flaws. Through painstaking calculations, meticulous observations, and a series of groundbreaking experiments, Einstein's theory began to emerge as a formidable contender, gradually outshining Newton's laws in its ability to explain certain cosmic phenomena that had long puzzled scientists. One of the most significant victories for relativity came in addressing a mystery that Newton's framework could not resolve: the peculiar orbit of the planet Mercury. According to Newton's laws of motion, an object moving in a vacuum, free from external forces, should maintain a steady speed and direction following a predictable path. Mercury orbiting the Sun in the vast emptiness of space should have adhered to a fixed elliptical orbit with no deviation over time. Yet astronomers had observed that Mercury's orbit was not static. It shifted gradually, a phenomenon known as the precession of its perihelion, which defied Newton's predictions. Einstein's theory of relativity offered a revolutionary explanation for this anomaly. He proposed that time and space are not separate entities, as Newton had assumed, but are instead interwoven into a single dynamic fabric known as space-time. Massive objects such as the Sun warp this fabric, creating a gravitational well that influences the motion of nearby objects. In this model, Mercury's orbit is not a simple ellipse, but a curved trajectory that shifts slightly with each revolution as it navigates the distorted space-time around the Sun. This insight not only explained Mercury's eccentric motion, but also provided a framework for understanding the orbits of all celestial bodies, revealing a deeper layer of reality that Newton's laws, while effective for many scenarios, could not fully capture. Far from contradicting Newton-Einstein's work, refined and expanded upon it, offering a more profound understanding of how objects move in a vacuum. This triumph earned relativity widespread acceptance among scientists, cementing its place as a cornerstone of astrophysics and a versatile tool for exploring the mysteries of the universe across a wide range of disciplines. However, this acceptance brought with it a new set of challenges as relativity's implications began to raise difficult questions about the nature of the universe itself. If Einstein's theory held that matter warps space-time to create the force of gravity, then why had the universe not collapsed under its own immense gravitational pull? To put it more precisely, if gravity were the sole dominant force acting on the cosmos, the universe born over 13 billion years ago should have long since contracted into a single massive entity, a dense singularity where all matter was compressed into an unimaginable void. Instead of the sprawling galaxies, radiant stars, and breathtaking nebulae that adorn the night sky, the universe should have become a silent, lifeless black hole devoid of light, motion, or existence. Yet here we stand, alive and breathing, gazing up at a sky filled with shimmering stars and colorful nebulae, a testament to the universe's enduring expanse. This glaring contradiction posed a profound challenge to Einstein's theory. If gravity was the only force at play, how could the universe remain as we see it? Does this suggest a fundamental flaw in relativity itself? To resolve this paradox, Einstein introduced a concept that would become one of the most debated ideas in the history of science: the cosmological constant, symbolized by the Greek letter lambda. This constant was intended to act as a counterforce to gravity, a repulsive energy that would prevent the universe from collapsing inward under its own weight. In essence, the cosmological constant proposed the existence of a force that pushed matter apart, counteracting gravity's relentless pull and maintaining a static, stable universe where celestial bodies could orbit indefinitely without falling into chaos. On the surface, this seemed like a stroke of genius, a clever adjustment to balance the cosmic equation and preserve the elegance of Einstein's model. However, in practice, the introduction of the cosmological constant felt like a makeshift solution, a patch applied to cover a gaping hole in the theory. What justified the existence of such a force? One that directly opposed gravity. Where was the evidence for this mysterious energy that seemed to exist solely to make the equations work? The introduction of the cosmological constant sparked immediate debate within the scientific community, raising doubts about whether relativity, much like Newton's laws before it, might be incomplete. Perhaps in our intricate and brilliant calculations we had overlooked a fundamental truth about the universe, namely that we are mere humans attempting to encapsulate the infinite complexity of the cosmos within the confines of our limited equations. Einstein might have been correct in theorizing that some force prevents the universe from collapsing, but he could also have been mistaken, underestimating the universe's vastness and the myriad forces at play beyond his mathematical models. Regardless of the outcome, the core mission of science remained unchanged: to experiment, to question, and to seek answers through evidence and reason. With the static universe model now under scrutiny, a new and pressing question emerged. If the universe is not static, as Einstein had assumed, then what is its true nature? Is it expanding, contracting, or following some other cosmic rhythm we have yet to comprehend? Einstein's theory of relativity had inadvertently rested on the assumption of a static universe, a cosmos where celestial objects orbited endlessly in a fixed dance, preserved by the cosmological constant to counterbalance gravity's pull. Yet this was not the first time such an idea had been proposed. Long before Einstein, other scientists had gazed at the heavens, pondering the apparent stillness they observed, questioning why everything seemed to remain in place. This simple curiosity should have sparked earlier skepticism. But perhaps we were too enamored with the notion of a perfect universe, a divine creation that mirrored our own ideals of order and harmony. In reality, however, the truth often defies our expectations, revealing a universe far more dynamic and complex than we could have imagined. The turning point in this journey came with the work of William Herschel, a German composer who turned his talents to astronomy and made a groundbreaking discovery in 1800: infrared radiation. This revelation shattered the old perceptions of light and energy, opening up new avenues of exploration that would transform our understanding of the cosmos. Herschel's discovery paved the way for other scientists to delve into the electromagnetic spectrum, a range of energy that spans from visible light to invisible waves, each defined by its frequency and intensity. Within the visible spectrum, light ranges from red, which has a lower frequency and weaker energy, to blue, which has a higher frequency and stronger energy. Beyond this visible range lie ultraviolet rays, which are stronger than blue light and can cause sunburn, followed by X-rays, which are used in medical imaging to peer inside the human body, and gamma rays, which are powerful enough to be harnessed in cancer treatments to destroy malignant cells. On the weaker end of the spectrum, beyond red light, we find infrared radiation, which we feel as heat, followed by microwaves used in household appliances, and finally radio waves, which enable technologies like broadcasting and communication. Astronomers quickly realized that this spectrum could be a powerful tool for studying the cosmos, particularly through a phenomenon known as the Doppler shift. When a celestial object emits light, the frequency of that light can shift, depending on the object's motion relative to the observer. If the object is moving toward us, its light is compressed, shifting toward the blue end of the spectrum, a phenomenon known as blue shift. Conversely, if the object is moving away, its light is stretched, shifting toward the red end, a phenomenon known as redshift. By analyzing these shifts, astronomers could measure the distance and speed of celestial objects, providing a window into the dynamics of the universe. In 1912, American astronomer Vesto Slipher made a startling observation while studying a faint speck of light in the night sky. This light exhibited a strong blue shift, indicating that the object was hurtling toward us at an astonishing speed of 3 kilometers per second. Such a velocity suggested that this object could not belong to our own Milky Way galaxy, and indeed it did not. It was the Andromeda Galaxy, a separate cosmic entity, a revelation that hinted at the existence of other galaxies beyond our own. Slipher's observations didn't stop there. Over the following years, he identified other galaxies exhibiting similar shifts, though their motions were not uniform. Some, like the Dreyer Galaxy, discovered in 1921, were receding from us at speeds of up to 2,000 kilometers per second. Their light redshifted as they moved away. If the universe were truly static, as Einstein had proposed, these galaxies should have followed predictable orbits, locked in a cosmic dance with fixed trajectories. Yet their erratic movements, some approaching, others receding, suggested a far more dynamic cosmos, one that was not fixed but in constant motion. This idea gained further support in 1922 when Russian astronomer Alexander Friedmann took Einstein's equations and expanded upon them, proposing that the universe could indeed be expanding. Friedmann went so far as to suggest that this expansion could be quantified, offering a mathematical framework to calculate its rate, though his work remained largely theoretical at the time. The true breakthrough came in 1929 with the work of Edwin Hubble, an American astronomer whose meticulous observations would forever change our understanding of the cosmos. Hubble, working at the Mount Wilson Observatory in California, used the powerful Hooker telescope, the largest of its time, to measure the distances to various galaxies and analyze the redshift of their light, building on the foundational work of Slipher. What he discovered was nothing short of revolutionary. The farther a galaxy was from us, the faster it was receding, as indicated by the degree of redshift in its light. This relationship, now known as Hubble's law, revealed a profound truth. The universe was not static, but expanding with space itself, stretching like a cosmic fabric, pushing galaxies apart at an accelerating pace. This expansion was not centered on us as if we were the focal point of the universe. Rather, it was happening everywhere, with every point in space moving away from every other point, a phenomenon that shattered Einstein's static model. Faced with this undeniable evidence, Einstein was forced to confront the reality that his cosmological constant and the static universe it supported was no longer tenable. The universe was not a fixed, unchanging entity, but a dynamic, expanding one, a realization that marked a turning point in cosmology. Einstein later described the introduction of the cosmological constant as his biggest blunder, a mistake that has since been etched into the annals of scientific history as a humbling reminder that even the greatest minds can err. Yet far from diminishing his legacy, this error opened a new chapter for global science, introducing two fundamental forces that shape our understanding of the cosmos: Einstein's gravity, which pulls matter together, and a mysterious, repulsive force later associated with dark energy that drives everything apart, fueling the universe's expansion. Hubble's discovery of an expanding universe set off a wave of excitement and curiosity among astronomers who threw themselves into research with the fervor of moths drawn to a flame determined to unravel the mystery of why the universe was expanding. To explain this phenomenon, scientists proposed the existence of dark energy and dark matter, enigmatic entities that might account for the unseen forces driving galaxies apart. Though these concepts remain speculative, serving as placeholders for phenomena we could not yet fully understand. The sheer scale of the universe suggested that we were still far from grasping its complete picture, with countless questions awaiting us on our journey to uncover its origins. This pursuit took an unexpected turn, leading to a revelation that came not from a scientist in the traditional sense, but from a Catholic priest raising profound questions about the intersection of faith and science. Could the universe's beginning be linked to a divine creator? A notion that had long been the domain of religion rather than empirical study. This tension between evidence-based science and belief-driven religion has fueled debates for centuries, often with tragic consequences for brilliant minds who never lived to see their ideas validated. Yet life is a tapestry woven with wonders, and in the early 20th century, the worlds of faith and evidence converged in a groundbreaking discovery tied to a cosmic explosion that would come to be known as the Big Bang. The question of why the universe exists at all has long perplexed philosophers and scientists alike, its immense vastness seeming to defy any simple explanation. For centuries, religions have offered answers attributing the creation of the cosmos to a supreme being, a divine force beyond human comprehension, responsible for bringing all things into existence. Science, on the other hand, has sought empirical evidence, often finding itself at odds with these spiritual narratives, creating a silent but persistent conflict between two ways of understanding the world. In the 1960s, two American physicists, Arnold Penzias and Robert Wilson, stumbled upon a discovery that would bridge this divide, offering a glimpse into the universe's ancient past. Working at Bell Telephone Laboratories in Holmdel, New Jersey, they were using a highly sensitive radio antenna to detect signals from space, hoping to advance communication technologies. During their observations, they noticed a faint, persistent radio noise that appeared in every direction they pointed their antenna, a signal so consistent that it seemed to be present 24 hours a day, 7 days a week. At first, Penzias and Wilson suspected that this noise might be the result of earthly interference, perhaps stray signals from nearby cities, the hum of passing airplanes, or even the droppings of a pigeon nesting on their antenna. They meticulously ruled out these possibilities, cleaning the antenna and eliminating all known sources of interference. Yet the noise persisted, as stubborn as ever. It was then that they realized the signal was not coming from Earth at all. It was emanating from the universe itself, a cosmic whisper that had been hiding in plain sight. This noise, they determined, was a form of ancient energy, a relic from a time long past. Much like the afterglow that lingers in our eyes after staring at a bright light, this energy had faded over time, but remained detectable, a testament to the immense power of its source. The scale of this residual microwave radiation suggested that it was the aftermath of a cataclysmic event, a blinding flash so powerful that it transformed matter into a state beyond our current understanding. Neither gas nor plasma, but something entirely unique, a form of matter that defies the definitions of modern physics. Penzias and Wilson named this relic the cosmic microwave background radiation, recognizing it as a faint echo of a massive explosion that occurred 8 billion years ago, an event that marked the birth of the universe itself. This discovery built upon earlier research into the nature of matter and its origins, a journey that stretches back to ancient Greece. Around 400 BCE, the philosopher Democritus proposed a radical idea that everything in the universe is made up of tiny, indivisible particles he called atomos, meaning uncuttable. This concept, though visionary, was met with resistance by other philosophers, most notably Aristotle, who argued that matter was not composed of particles, but was instead a continuous substance divisible infinitely and made up of elemental forces like fire, air, water, and earth. Aristotle's view dominated for centuries, but Democritus's idea of atoms eventually resurfaced, becoming a cornerstone of modern science as we developed a deeper understanding of the building blocks of matter. One of the most pivotal figures in this journey was Georges Lemaitre, a Belgian priest and physicist born in July 1894 to a devout Catholic family. From a young age, Lemaitre displayed an extraordinary aptitude for science and mathematics, a talent that would shape his destiny. In 1911, he enrolled at the Catholic University of Leuven to study natural sciences, but his education was interrupted by the outbreak of World War I. Drafted into the military, Lemaitre served on the front lines, yet even amidst the chaos of war, his mind remained fixed on the mysteries of the universe, using his downtime to ponder cosmic questions that would later define his career. After the war, he returned to his studies, completing his degree, and later traveling to Cambridge, where he studied under Arthur Eddington, a pioneering physicist who had been instrumental in validating Einstein's theory of relativity. Lemaitre went on to earn a doctorate in physics from MIT, but his journey took a unique turn when he was ordained as a Catholic priest by Cardinal Désiré Joseph Mercier, blending his scientific pursuits with a deep faith in God, a combination that would prove both controversial and inspiring. In the 1920s, Lemaitre joined the faculty of the Catholic University of Leuven as a professor, where he began to explore the implications of Einstein's static universe model. At the same time, Edwin Hubble was making his groundbreaking observations of galactic redshifts, providing evidence that the universe was expanding. Lemaitre, however, took a different approach, diving deeper into the mathematics of Einstein's general theory of relativity to understand its broader implications. He noted a fundamental contradiction: if gravity were the only force governing the cosmos, as Einstein's model suggested, then the universe should be contracting, not expanding, as matter would inevitably be pulled together by its own gravitational attraction. The fact that the universe was expanding, as Hubble's observations confirmed, suggested that there must be another force at play, or more intriguingly, that the universe had a beginning, a point from which this expansion originated. Lemaitre proposed a revolutionary hypothesis. The universe began as a single, infinitely dense and infinitely hot point, a singularity he called the primeval atom. From this point, he argued, the universe burst into existence through a massive explosion, releasing all the matter and energy that would eventually form the galaxies, stars, and planets we see today. This explosion, which Lemaitre termed the initial quantum, would have left behind a detectable signature in the form of residual radiation, a prediction that would later prove to be astonishingly accurate. Lemaitre first published this idea in 1927 in the relatively obscure journal Nature, where it went largely unnoticed by the broader scientific community. However, in 1931, he expanded on his hypothesis, presenting a more detailed vision of a universe that began with a colossal explosion, an event that would come to be known as the Big Bang. He argued that this explosion would have scorched space-time, leaving a fading imprint that future generations might one day detect provided science advanced enough to observe it. Lemaitre's theory, though visionary, was met with significant skepticism. Many scientists at the time were reluctant to accept the idea of an expanding universe, clinging to Einstein's static model as the prevailing paradigm. Others were uncomfortable with the notion of a cosmic beginning, as it seemed to align too closely with religious ideas of creation, suggesting that the universe might have been initiated by a divine force, a concept that clashed with the ideals of empirical science. Even Einstein himself dismissed Lemaitre's hypothesis, reportedly describing it as theoretically plausible but practically absurd. Yet as Hubble's observations of galactic redshifts provided irrefutable evidence of cosmic expansion, and Penzias and Wilson's 1965 discovery of the cosmic microwave background confirmed the presence of the radiation Lemaitre had predicted, the scientific community was forced to reconsider. The Big Bang theory, born from the mind of a priest scientist, gained widespread acceptance, becoming a cornerstone of modern cosmology and a testament to the power of blending faith and reason. The Big Bang marked the birth of the universe as we know it, a singular event that unfolded from a point of infinite density and heat, a singularity smaller than the core of a black hole, hotter than anything we can imagine, and existing in a state where neither time nor space had yet come into being. In that moment, all the matter and energy that would eventually form the cosmos was compressed into this single point, a cosmic seed containing the potential for everything that would follow. Then, in an instant, this singularity erupted in a cataclysmic explosion, releasing its contents in a blinding flash that marked the beginning of time and space themselves. The intense heat of this explosion scorched the nascent space-time, leaving behind a fading imprint, the cosmic microwave background that we can still detect today, a whisper of the universe's violent birth 13.8 billion years ago. In the first fleeting moments after the Big Bang, the universe was a seething, ultra-dense sea of energy, far too hot and chaotic for matter to exist in any recognizable form. As the universe expanded, this energy began to cool, allowing particles to form and interact in the rapidly expanding space. Within the first few seconds, a process known as nucleosynthesis began as protons and neutrons collided and fused, forming the lightest elements, hydrogen and helium, which would later become the building blocks of stars and galaxies. Over the next few 100,000 years, the universe continued to cool and expand, allowing more complex interactions to take place. As the temperature dropped heavier, elements began to form their gravitational pull, drawing matter together into clumps that would eventually coalesce into the first stars and planets. At the same time, the universe's expansion allowed light to travel freely for the first time, transforming into the microwave radiation we now observe as the cosmic background, a snapshot of the early universe frozen in time. This model of cosmic evolution, known as the Big Bang theory, provides answers to many of the fundamental questions about the universe's structure and history. It explains the presence of the cosmic microwave background, the abundance of light elements like hydrogen and helium, and the large-scale structure of galaxies and galaxy clusters we observe today. However, some questions remain unanswered, such as the precise rate of the universe's expansion, a value known as the Hubble constant, which continues to be a subject of debate among scientists. Despite these uncertainties, the Big Bang theory has proven to be a robust framework serving as a foundation for further research and inspiring generations of scientists to explore the cosmos in greater depth. Yet the implications of the Big Bang Theory have not been without controversy, particularly among scientists who grapple with its philosophical and scientific ramifications. One of the most troubling aspects for some is the theory's suggestion of a cosmic beginning, a moment of creation that seems to echo religious narratives implying the existence of a divine force that set the universe in motion. The initial conditions of the Big Bang occurring at a point where the laws of physics as we know them break down cannot be directly observed or tested, making them difficult to study empirically. This limitation has led some scientists to question whether the Big Bang truly represents the ultimate origin of the universe, or whether it might be part of a larger cycle. An alternative hypothesis known as the Big Bounce suggests that the universe undergoes a series of expansions and contractions, with each Big Bang followed by a collapse into a new singularity, only to explode again in an endless cycle. This model avoids the need for a divine creator by proposing that the universe has always existed, cycling through phases of expansion and contraction without a true beginning or end. Despite these debates, the evidence for cosmic expansion, bolstered by Hubble's observations, the cosmic microwave background, and other measurements, remains overwhelming, making the Big Bang the most widely accepted explanation for the universe's history. Georges Lemaitre's contributions, alongside those of Edwin Hubble, have left an indelible mark on cosmology, earning them recognition as the fathers of the modern understanding of cosmic expansion, now enshrined in the Hubble-Lemaitre law. Remarkably, Lemaitre remained a humble figure throughout his life, continuing his work as a researcher and professor at the Catholic University of Leuven, eschewing fame and recognition. He passed away in 1966, just 1 year after the discovery of the cosmic microwave background provided ironclad evidence for his predictions, a fitting capstone to a career that bridged the worlds of science and faith. The 20th century marked a golden age for science, with Einstein's theory of relativity and the development of quantum mechanics providing powerful tools to understand the universe at both the largest and smallest scales. Relativity allowed us to predict the motions of stars and planets with unprecedented accuracy, while quantum mechanics revealed the strange and probabilistic world of subatomic particles, offering insights into the fundamental building blocks of matter. Together, these theories seem to provide a comprehensive framework for understanding reality, from the vastness of galaxies to the intricacies of atoms. Yet a closer examination revealed a troubling inconsistency. Relativity and quantum mechanics, despite their individual successes, are fundamentally incompatible, operating on principles that do not align and often producing conflicting predictions when applied to the same phenomena. This incompatibility has given rise to one of the greatest challenges in modern physics, the search for a unified theory, often referred to as the Holy Grail of science. A unified theory would merge relativity and quantum mechanics into a single cohesive framework capable of explaining all physical phenomena, from the motion of galaxies to the behavior of subatomic particles. However, achieving this synthesis is no easy task. Relativity treats time and space as a single continuous entity, space-time, that is warped by massive objects to create gravity. Quantum mechanics, on the other hand, treats time and space as separate entities, describing particles like electrons as clouds of probability, their positions and behaviors governed by the strange rules of quantum uncertainty. For example, in the quantum model of an atom, the nucleus is not a single solid particle, but a collection of smaller particles called quarks, held together by the strong nuclear force mediated by gluons. Electrons, meanwhile, do not orbit the nucleus in fixed paths. as planets orbit a star, but exist as probabilistic waves, their exact locations impossible to pinpoint without measurement. Bridging these two frameworks requires reconciling their fundamental differences, a task that has eluded even the greatest minds in physics. One proposed solution involves the concept of a hypothetical particle called the graviton, which would mediate gravity in the same way that gluons mediate the strong force in quantum mechanics. However, gravity is not a force in the traditional sense. It is the curvature of space-time caused by mass as described by relativity. This distinction makes it difficult to integrate gravity into a quantum framework, prompting scientists to explore alternative theories that might encompass both relativity and quantum mechanics. One of the most prominent candidates is string theory, which posits that the fundamental building blocks of the universe are not particles, but tiny vibrating strings whose oscillations give rise to the various forces and particles we observe. While promising string theory remains untested experimentally, existing primarily as a mathematical framework with countless equations, a testament to the complexity of the challenge. The quest for a unified theory underscores the limits of our current understanding, highlighting the vastness of the unknown in our exploration of the cosmos. Yet another debate has emerged alongside this scientific pursuit, one that delves into the philosophical implications of the universe's structure, the fine-tuning argument. This argument centers on the observation that many of the fundamental constants of physics values, like the cosmological constant, the gravitational constant, and the Planck constant, appear to be precisely tuned to allow for the existence of life. The cosmological constant, once dismissed as Einstein's blunder, has been repurposed to measure the influence of dark energy, the mysterious force driving the universe's accelerated expansion. This constant is extraordinarily small, yet just large enough to shape the cosmos as we know it. If it were slightly larger, the universe would expand too rapidly for galaxies to form. If it were slightly smaller, gravity would dominate, causing the universe to collapse before life could emerge. Similarly, Earth's position in the universe seems remarkably suited for life. Our planet orbits the Sun at a distance of approximately 151 million kilometers, a distance that varies slightly but remains within a range that allows for liquid water, a prerequisite for life as we know it. If this distance were increased to 155 million kilometers, Earth's temperature would drop, potentially freezing all water and rendering life impossible. Earth's crust, too, is finely balanced with a thickness of 15 to 20 kilometers that is both hard enough to stabilize geological activity and soft enough to allow tectonic movement, facilitating the cycling of nutrients essential for life. The Sun itself is a main sequence star, neither too large nor too small, with a diameter of 1.39 million kilometers and a mass 109 times that of Earth, providing just the right amount of energy to sustain life without incinerating the planets around it. Other constants, such as the structure of water molecules, 2 hydrogen atoms bonded to 1 oxygen atom, allowing water to exist as a solid liquid, and gas further suggest a universe tailored for life. The gravitational constant determines the strength of gravity. The electromagnetic constant governs the force of electromagnetism, and the ratio of the strong nuclear force to the weak nuclear force, which is approximately 101, ensures the stability of atomic nuclei. These values, among countless others, appear to be calibrated with astonishing precision, leading some to propose the idea of a grand designer, a cosmic architect, who set these constants to enable the emergence of life. This concept, often referred to as the fine-tuning argument, has sparked intense debate, as it seems to echo religious ideas of creation, challenging the empirical foundations of science. However, not all scientists are convinced by the fine-tuning argument. Critics argue that these constants might simply be the result of chance discovered through observation rather than design, and that our existence as observers biases us towards seeing the universe as special. As astronomer Carl Sagan famously noted, "The absence of evidence is not evidence of absence." If we assume that we are the chosen ones uniquely positioned to exist because of these constants, we risk overlooking other possibilities, such as the existence of life elsewhere in the universe, perhaps in forms we cannot yet imagine. The universe is far too vast for us to conclude that we are the only ones capable of existing under these conditions, and our current evidence is limited to our own existence, making it difficult to draw definitive conclusions. The fine-tuning debate thus remains a point of contention, a reminder of the delicate balance between science and philosophy, between what we can prove and what we can only ponder. The story of the Big Bang and the debates it has inspired offer a profound glimpse into humanity's quest to understand the universe and our place within it. The Big Bang theory, supported by evidence like the cosmic microwave background and the observed expansion of the universe, provides a compelling narrative for the cosmos's origins, explaining the formation of galaxies, stars, and planets through a series of well-documented processes. Yet it also raises questions that challenge our understanding, from the nature of the universe's initial conditions to the possibility of a grand designer behind its precise constants. The search for a unified theory merging relativity and quantum mechanics continues to push the boundaries of science, while the fine-tuning debate invites us to reflect on the deeper implications of our existence. Science at its core is a process of exploration and discovery, a journey marked by both triumphs and uncertainties. The Big Bang, relativity, and quantum mechanics are not endpoints, but stepping stones, each revealing more of the cosmic puzzle while hinting at deeper truths yet to be uncovered. Whether the universe's fine-tuning points to a grand designer or is simply the result of chance, our pursuit of knowledge remains driven by curiosity, wonder, and a relentless desire to understand. The cosmos is vast, complex, and filled with mysteries that may take generations to unravel, but it is precisely this vastness that inspires us to keep searching, to keep questioning, and to keep dreaming of what lies beyond the stars. As we reflect on this journey, we are reminded of the words of the scientists who came before us. Figures like Einstein, Hubble, and Lemaitre, whose contributions have shaped our understanding of the universe. Their work, though groundbreaking, was not without flaws, a testament to the iterative nature of science, where each discovery builds on the last, refining our knowledge and pushing us closer to the truth. The Big Bang Theory, with all its implications, is a testament to this process, a story of how humanity has sought to understand the cosmos through reason, evidence, and imagination. And while we may not have all the answers, the journey itself is a remarkable one, a testament to the enduring human spirit and our unyielding quest to explore the unknown.
Thanks for watching this video. If you like this video, drop a comment below. And please like, share, and subscribe my channel.